This week I thought we'd talk about the diaphragm. I was giving a lecture on the embryology of the lungs and the respiratory tree and stuff this week, in which we talk about how the diaphragm develops because it's important in separating off this original single cavity that the embryo has into two, and then into the lungs developing and stuff. And if it doesn't separate off, if the diaphragm doesn't form, you get problems. Anyway, we're not doing embryology, we're doing anatomy. So let's do the anatomy of the diaphragm because we haven't done it before. I got these, but I know I've also got this model here, which is quite nice. It has a diaphragm on it. So we should talk about its functions, because I'm sure you know about the diaphragm and its role in respiration, but it does other things as well. We should talk about its structure. This being an anatomy video, it'd be a bit daft if we didn't. Structure, it's a musculotendinous thing, where it's attached, the three big structures that pass through it and how they pass through it, how it's attached to things, and we should talk about its innervation and its blood supply. That sounds pretty thorough, right? We'll chuck in some clinical smatterings towards the end. So the diaphragm is like a domed thing. It's kind of a double dome, really, and it's up in here, within the rib cage, and as I was saying, it's mostly muscular with this central tendon, and we'll talk about the different parts as we go. But that double dome, by the way, we're a couple of weeks away from yet another exam, which means there's lots of students studying. So if you hear noise, it's students studying. This isn't a very soundproof room. I haven't got a soundproof room. Anyway, I'll just try and talk over them. So this double dome, the muscles contract and the dome flattens somewhat. And you guys, I imagine you're not out jogging or anything while you're watching this video. If you are, watch out for lampposts. You're probably sat down, not burning a lot of energy, and your diaphragm is gently rising and falling, and that is your main muscle of respiration. It's the main muscle of inspiration. So when this dome, is this going to fall apart now? When this dome pulls down and flattens, the volume inside the thorax increases. With that increase in volume is a decrease in pressure. So to equalize that pressure, air is drawn into the lungs. With expiration, it's mostly the diaphragm doesn't really have to do much. The diaphragm relaxes, and the muscle, of course, the lungs are they're full of elastic material. So when you exhale, it's a very relaxed action because the lungs shrink, the diaphragm relaxes, and so on. Which is why we say that the diaphragm is the main muscle of respiration, because it does inspiration and then relaxation lets you breathe out. So the diaphragm flattens somewhat during inspiration, increasing the volume in the thorax, and if it increases the volume in the thorax, then it's going to have to push down on the abdomen. So the volume of the abdomen kind of increases a little bit. But of course we haven't got the rib cage down here, which means the abdomen can change its size more easily. So when we talk about belly breathing, what we're talking about is the diaphragm pulling down and flattening and pushing all the contents of the abdomen out. Right. If you watch cyclists in the Tour de France or something similar, these super skinny guys, you know they're crazy lean guys, but as they're going up a mountain and breathing through their ears, you'll see they develop a belly. The reason they develop a belly is because they're breathing so hard, they're pushing their abdominal contents out. Of course, they're hunched over a little bit, and they got lots of lycra on, right? So they look like they're developing bellies, but they're not. That's belly breathing. So it's the diaphragm moving down. Now, if I take the lungs off here, you can see quite clearly that the heart, in fact, surrounded by pericardium, sits on the centre of the diaphragm, which means actually that double dome shape of the diaphragm is somewhat flattened towards the middle, where the heart and its pericardium lie upon it. And under here, we have the liver. And the liver is kind of pushing the right dome a little bit higher than the left dome. But all of these things, and this is the plastic model that doesn't move, but you've got to remember that in biology, as the diaphragm is moving, all of these other things are moving as well. So the heart is going up and down, the liver's being pushed down, the stomach's over here, the lungs are obviously changing in size and that sort of thing. So there are no spaces in here, everything's packed together. So as the diaphragm moves, the liver gets pushed down, the heart gets pulled down, and then everything goes back up again. Which means that if you're trying to, if you're trying to image this area, if you stick someone in an MRI scanner and trying to image this area, it's very difficult because everything's moving, nothing stays still for long enough. Anyway, so the other important effect then of the diaphragm is that if it pushes down into the abdomen, you can use it to increase your intra-abdominal pressure or your intra-abdominopelvic pressure, which is very useful when you're trying to squeeze things out of the abdomen and the pelvis, like vomit and feces and babies and things like that. I was in the gym this morning. I wasn't expelling vomit or feces, but I was doing leg day today, so I was doing deadlifts and what have you. And you get really out of breath, they're really hard, partly because you're using massive muscle groups, but partly also because you're using the diaphragm to increase the pressure in your core, in your trunk, to make a solid thing that you can use to lift heavy weights, which gets you a bit out of breath, So you don't really want to, I know some people hold their breath, but you kind of increase the pressure. So the abdomen, the diaphragm also gets used in controlling and increasing the abdominal pressure for lifting heavy weights, expelling things from the abdomen and the pelvis and that sort of thing. Okay, that's functions. Any other functions? Hiccups? Laughing? They're all related, right? Right, structurally then, the diaphragm is muscular around the periphery and more tendinous towards the center. So this central aponeurosis, this kind of flattened tendon that we see here, gets called the central tendon of the diaphragm. And you get an idea here, you can see three things passing through the diaphragm at different levels, and we'll meet each of one of those in turn. But the diaphragm then it's anchored in here, and essentially it's anchored to the inferior 6 ribs, so ribs 7, 8, 9, 10, 11, 12, and the xiphoid process, and the lumbar vertebrae down here. And the different parts get described. The other thing I want you to think of is that inside the thorax here, it's not a neat oval. Remember that the vertebrae are pushing outwards anteriorly into the thorax, which means that the shape of the diaphragm also isn't like a perfect oval. It is then instead that shaped, right? So the vertebrae are pushing into, so it's kind of a, that sort of shape, all right? I just wanted to keep that in your head when you're thinking about the diaphragm and the shape of the posterior thoracic wall. So there are 4 parts to the diaphragm. If we have that central tendon, the diaphragm is anchored anteriorly by a sternal part which attaches to the inferior surface of the xiphoid process. This is the xiphoid process of the sternum here. And then it has a costal part, so kind of this bit running around here, and this part of the diaphragm is anchored to the costal cartilages and the ribs of the inferior 6 ribs. Like I said, so posteriorly we have these floating ribs, 12 and 11, but we have 7, 8, 9, 10, 11, 12, right? So it's anchored to these ribs here. And then posteriorly, it's anchored to the first 2 or 3 lumbar vertebrae. There seems to be some variation here. And in here we find the medial and lateral arcuate ligaments, we'll talk about those in a moment, which it's anchored to. And here we find the crura, these 2 long slips anchoring the tendon, anchoring the diaphragm posteriorly here. So we have the sternal parts, the costal part, costal referring to ribs, and then we have the lumbar part anchored to the lumbar vertebrae. All right, okay, so posteriorly we've got some interesting stuff going on. Right, what do we got? Right, you know how muscles are wrapped in fascia and layers of the body are kept separate by layers of fascia, right? Here, this is psoas major, Flexor of the hip, running from the vertebrae down there. There's quadratus lumborum, again running up to the vertebrae over there. Now, these guys are covered in fascia, and where that fascia thickens, they form what we call arcuate ligaments. Arcuate? Arching? Maybe. Because the way, you can't see it here because it's deep to the kidneys, but as these go up here, the quadratus lumborum muscle is covered by the lateral arcuate ligament, and the psoas major muscle is covered by the medial arcuate ligament. So that's the fascia forming a thickening up under here somewhere. And those thickenings, those arcuate ligaments, act as anchors for the diaphragm, and the anchors are here. These are the crura, the left and right crus. These are muscular structures running from the first couple of lumbar vertebrae, and they're running up to form the posterior, to anchor the posterior part of the diaphragm here. And look, you can see the aorta running between those two crura, running in the gap there. So those are the medial and lateral arcuate ligaments. Now, where the two crura meet here, where they come together, that gets called the median arcuate ligament. Median being in the midline, so lateral, medial, relative to one another, median being in the midline, well, pretty much the midline anyway. So that's the median arcuate ligament there. And then these two, you can see the crura, the left and right crus of the diaphragm running up and then inserting again into the central tendon up here. Now look, there's the esophagus there. Can you see the direction of the muscle fibres? So the muscles of the right crus is actually, its fibres are running over that way, and the left crus, left, right, the left crus is running over that way. So the muscle fibres of the two crura are also forming another gap for the esophagus. This is the esophageal hiatus. And it forms kind of a bit of a sphincter. But you know a really good sphincter is like a ring of muscle? And we haven't really got a ring of muscle there, but we've kind of got a ring of muscle, so we've kind of got a reasonably good sphincter here. And that esophageal hiatus, along with various other physiological things and other structural things where the esophagus meets the stomach, forms a reasonably good sphincter between the esophagus and the stomach, stopping stuff in the stomach from going back up into the esophagus. It doesn't work very well. You get reflux, you get acid reflux going up into the esophagus and causing a bit of pain when you eat and that sort of thing, right? You might take antacids for it. So that's why that problem occurs, is because there's not a proper sphincter there. There's like a reasonably good one. So this esophageal hiatus gets squeezed when the diaphragm contracts. So the aortic hiatus is actually a gap between the two crura. Movements of the diaphragm don't affect the aorta, I think. The esophagus passes through the esophageal hiatus. The movements of the diaphragm do affect the esophagus. And here, there's another hole there, incomplete because I've taken part of the model apart, but that is the hiatus for the inferior vena cava. And look, because the heart is sat and its pericardium is anchored to the diaphragm, the inferior vena cava passes through the diaphragm and then it's straight into the right atrium. It's straight into the heart there. And I've read various things about how movements of the diaphragm affect the inferior vena cava. I mean, there was the idea that because the inferior vena cava is attached to the diaphragm, that actually holds the inferior vena cava open and makes it easier to draw blood back. Well, that's the other thing. Movements of the diaphragm, changing the pressure in the thorax, also help draw blood back into the thorax, right? Anyway, I also read some conflicting stuff about how maybe... anyway, forget that. Right. So the one thing that we ask students to remember is the levels of each of these hiatuses. And the vena cava has 8 letters, and the hiatus of the inferior vena cava occurs around the level of the T8 vertebra, maybe the T8, T9 intervertebral disc, whatever. T8, 8 letters, right? The esophagus, if you spell it with the British spelling, O-E-S-O-P-H-A, esophagus, that has 10 letters, and that passes through the diaphragm at around T10, vertebral level. And the aorta has got 5 letters, so that passes through the diaphragm at about the T12 level. Sorry, doesn't work perfectly, but you know, right, 8, 10, 12. Aortic hiatus, A-O-R-T-I-C-H-I-A-T-U-S. Aortic hiatus would work, that's got 12 letters. I might be confusing you, sorry. So this gets called the caval opening, this esophageal hiatus, and the aortic hiatus. Those are the 3 big structures that pass through the diaphragm. Now, what about the little structures that pass through the diaphragm through the same holes? There is another little hole as well somewhere, but I'll leave that up to you. You can work out what big cranial nerve runs with the esophagus, right? For example. Because that goes, anyway. Right. Blood supply. Well, most straightforwardly, first concept is that the superior diaphragm has some blood vessels and the inferior diaphragm also has some blood vessels. So the superior diaphragm receives some superior phrenic arteries, which are branches off the aorta, which makes sense. It also receives the internal thoracic arteries are running right down here, right on the where are you? The internal thoracic arteries are running on the internal surface of the thoracic cage, and those give off some pericardiophrenec and musculophrenic arteries to the superior part of the diaphragm. So the inferior surface has inferior phrenic arteries, and those can come from the aorta or they can come from the first anterior branch of the aorta. Do you remember these 3 guys supplying blood to the GI tract? So the celiac trunk is here supplying blood to the foregut. That can also give off inferior phrenic arteries. So inferior and superior phrenic arteries supply blood to the diaphragm, and they can come from number of places, right? Venous drainage is similar. You have inferior and superior phrenic veins, and those can drain directly to the inferior vena cava. They can drain to the azygos and hemiazygos veins, to the azygos system, and stuff like that. I think they can drain to the renal veins and back to the inferior vena cava, but you get the idea. Drains to the inferior vena cava or azygos veins. Remember the azygos veins? They go up to the superior vena cava. Phrenic. Now there's a thing. Phren kind of refers to the mind, right? Phren, that sort of word, phrenic. How does phrenic both refer to the mind, and to the diaphragm? Well, not sure. It certainly seems to come from the ancient Greeks, and the ancient Greeks weren't terribly sure either. There were a couple of different camps. The ancient Greeks had a great time philosophizing and working out what was going on in the body, right? And they believed, or some of them believed, Plato and Aristotle maybe, some of them believed that there were 2 souls. You kind of had your spiritual soul and your physical soul, like your immortal soul and your mortal soul. And your immortal soul was up here, and your mortal soul, so your spiritual soul up here, and then your physical soul was down here. So the diaphragm played a role in keeping the mortal soul away from the immortal soul. It's a nice idea, I like that. So immortal soul, phrene being related to the head and what have you. And they also talked about the heart, the heart being kind of the seat of emotion, the seat of consciousness, but the seat of that immortal soul, the spiritual soul, which you can kind of imagine with the motion and that sort of thing, right? Whereas down here in the abdomen is involved in very physical, mortal things. It digests food and expels waste and that sort of thing. And you wouldn't want that to muddy the spiritual stuff up here. So they had the word Phrene, and even that, of course, is an anglicised spelling. It's not the ancient Greek, is it? But how would that be pronounced? Phrene. I mean, it's ancient Greek and Latin. Do we really know how it was spoken? Because, of course, there are no recordings from that time. But that's why the word phrenic, relating to structures of the diaphragm, also gets related to structures of the mind because of that ancient Greek idea. Some of the Greeks disagreed with that and they thought the diaphragm did the things that it does. But it's always good to discuss these things, isn't it? Right, and that leads us to the phrenic nerve, doesn't it? So the nerve that innervates the diaphragm is the phrenic nerve. The interesting thing about the phrenic nerve is it actually comes from the neck. C3, 4, 5 keeps the diaphragm alive, we say, because it's mostly C4, but C3, 4, 5 spinal nerves come together to form the phrenic nerve, and the phrenic nerve it pops out between the scalene muscles, which I haven't really got any here. So the phrenic nerve pops out from between the scalenes. There are 3 muscles running from the cervical vertebrae down to the first couple of ribs. But you typically describe the phrenic nerve as being found on the anterior surface of the anterior scalene muscle, and then it runs down into the thorax. So whenever we're dissecting, we often find them blending with the fibrous pericardium. As we dissect the fibrous pericardium, we find the phrenic nerves. So the right phrenic nerve runs over the right atrium, and it tries to get down to where the inferior vena cava is passing through that caval opening, and the left one passes kind of over the left ventricle to get down to the diaphragm. And they do pass through the diaphragm, so they innervate both surfaces. So the phrenic nerve is the motor supply to the diaphragm. So if you damage one of the phrenic nerves on one side, there will be paralysis of a hemidiaphragm. There'll be paralysis of the diaphragm on one side, which is not a good thing. But that also explains why, because they're sensory also from the diaphragm and from the fibrous pericardium and bits of the pleura around here, like the mediastinal pleura. Pain from the diaphragm can get referred up to the shoulders. I'm sure you're all runners, right? You run a lot. You maybe have had a stitch in your time. The stitch may be related to the liver hanging off the diaphragm, and the pain is localized maybe to start with, but then it moves towards the shoulder. Well, the periphery of the diaphragm, the muscular periphery around here, is also innervated by the intercostal nerves in between the ribs, and also the subcostal nerves down here. So the periphery gets innervated by those as well as the phrenic nerve, and those carry sensory stuff back. But you get pain locally, but then you seem to get referred pain up to the shoulder, and the reason why is because as the diaphragm gets irritated, the phrenic nerve carries that sensory innervation back up here to the spinal nerves of the neck, and the brain perceives that pain as coming from the nerves of the shoulder region, which are also coming from the shoulder. Perceiving visceral pain is difficult. Perceiving somatic pain and sensation is very normal. We've grown up learning how to do it. All right, nerves, arteries, Are we getting there? Yeah, so now you know the shape of the diaphragm. You know it's 4 parts. Those are the kind of 4 parts. It's got more than 4 parts, but you know what I mean. The 3 anchoring regions, and then the central tendon. We've talked about the 3 big holes in it, and the 3 big structures that pass through it, leaving you to work out what the little structures are. We've talked about how it moves and its functions, its innervation, its blood supply. All right, hopefully that was helpful. A few clinical things then. Did I talk about hiatal hernia or hiatus hernia? Yeah, I talked about esophageal reflux, didn't I? But if the esophageal hiatus is really not working very well, then abdominal pressure can actually push the stomach, or part of the stomach rather, and the inferior part of the esophagus back up through the esophageal hiatus into the thorax, which makes that whole reflux thing even more likely, causing more pain. So that's a hiatus hernia, and that's because we haven't got a brilliant sphincter there. Congenital diaphragmatic hernia, that was one of the things I was leading towards when I was talking about the embryology of this. So the diaphragm embryologically forms from 4 parts really coming together, and if that doesn't work properly and there's a gap left in there, then as the contents of the abdomen are forming and the contents of the thorax are forming, the contents of the abdomen tend to win because they grow larger faster, and they push up into the thorax and they fill the space up here, passing through that congenital diaphragmatic hernia. And that's terrible because the lungs will grow to fill the space that's available to them. So if there isn't space available to that lung, then that lung won't develop. So that's bad. Other hiccups. When you hiccup, that's your diaphragm spasming. That's a nicer clinical thing. Not so nice if you have permanent hiccups, I suppose. Right, there you go then. The diaphragm, anatomy of. See you next week. If I don't see you in the vlog before then.